we are going to have a look at the moment. And the moment when we talk about the moment, it's very important that we start to define a few things. One, we have to know what is a lever. We have to know what we say when we talk about the fulcrum. We also have to define the machine. So a lever is a bar, is a rigid bar. It's a rigid bar. Is a rigid bar that can be turned around a point that can't be turned around a point. This is a bar, and we can illustrate the bar. It's I have this here, and on top of this, I have on top of this, I have a stone here, and then for me to lift this stone, I need to exert the force here. I need to exert the force here. And then that is only possible if there is a point of support somewhere there, which I'll call the fulcrum. Now, if this is if the whole system I have here is on the ground, if the whole system here is on the ground, let's expect that to be bigger, that it is a bigger stone, and that will be our fulcrum there. And this will be our lever. Now, a machine, you also have to know what's a machine. Now, a fulcrum gives us the support supported there. So a machine is a device. A machine is a device A machine is a device which you can apply a force at a particular point to achieve a motion at the other point. Now, if I apply a force here, this stone here will move. So I will experience a motion at that other point. So basically, a lever is the simplest form of a machine. Now, this machine here has what you call a turning effect, called a moment of a force. Now, we said through that, this brings about a turning effect. Now, if I have two little kids playing there, now you'll appreciate that at one stage you find that one child is there, other one is there. And the second stage is the reverse. This one will be down, this one will be up. Now, this is called a moment of a force. Now, from this position here, from the fulcrum to this point here, now there's a distance from the fulcrum perpendicular to the weight of this little boy here. Now, I hope you appreciate that weight is measured in Newton. Then that's a force that is the product of the mass of a boy and gravitational acceleration towards the center of the earth. So that force will be pointing down as our weight. And then the force, which is the force multiplied by that perpendicular distance, constitute the moment. That will constitute the moment from the fulcrum. Now, if you look at this, you'll appreciate that. Let's draw another one here and see what happens. And we have those two forces. One down. Now, if you have a clock here, that would be a 12, the 3, the 6, and the 9 here. Now, I hope you'll appreciate that if you move in this direction, it's called clockwise direction. And if you move in that direction, it's anti-clockwise. Anti-clockwise. Now, that being the case, I hope you appreciate that this kind of force here and the distance from the fulcrum, which is called that, this will produce the anti-clockwise moment. Anti-clockwise. And then this one goes that way. This one will produce a clockwise movement. This will choose a clockwise moment. Now, if this distance here is the same as that distance there, and the forces are the same, say 2F here, 2F here, we will have the clockwise moment equal to the anti-clockwise moment and this will constitute what you call equilibrium. Now, a system of forces in equilibrium is basically the sum of the clockwise moment about this point here, fulcrum, and that should be equal to the sum of the anti-clockwise moment about the same point. That constitutes equilibrium. Now, we use the law of equilibrium to calculate either a particular distance or a particular needed force, or the amount of the force, the quantity of the force applied there. Now, I hope here you'll appreciate that for this moment here and that moment there, I will have the force, which is 50 Newton, multiplied by 2 meters. And this should equal to this side here, I have 15 Newton, multiplied by 2 meters. And that gives you 30 Newton meter, which is basically equal to the clockwise movement, 30 Newton meter. This one here is clockwise. This one here is anti-clockwise. Now, let's go and have a look at another situation. This situation here, where our interest lies there. I hope you appreciate that for the force of 60 Newton at that point will give us the anti-clockwise moment. And this anti-clockwise here will be 60 Newton multiplied by 3 meters. This should equal to this force here, that is 20 Newton multiplied by 4 meters. plus the distance from this point of turning point here, perpendicular to that force there, is 5 meters, and is F times 5 meters. I hope you appreciate that this is 5, 4 plus 1. Now 6 times 3 is 18. We have 180 Newton meter, which is equal to 4 times 20 is 80 Newton meter, plus 5 mf. Transposing this, we have 180 minus 80. All this is Newton meter, will equal to 5 meters at the F. This gives us a difference of 100 Newton meters. Is equal to 5 meters F. Divide by 5 meters on the right hand side. You do that. On the left, what you do, the basic rule of an equation. What you do on the left, you do on the right. 5 here, that will be 20 Newton. Because you'll appreciate that the meter will drop with the meter. So it means here we have a force of 20 Newton. Now, I hope we can have a look at the last one here. Our point of interest should be here, of course. Now, from here, this will go that way, which is anti-clockwise. These ones go down this way, is clockwise. So the anti-clockwise is equal to clockwise. So it's better when we say F multiplied by the whole of this distance here, that is 3.2, 4.2 meters, is equal to 10 kilonewton multiplied by 1 meter. Now, the distance from this point here to where the force is applied is 1 meter. This distance here is perpendicular to the force. Don't forget that. Plus, this one here is 20 times 20 kilonewton. You multiply by 3.2 meters plus 5 kilonewton multiply by 4.2 meters. So all what is left is for us to do some arithmetic. This will be 10 kilonewton plus 2, this is 4, and that is 6, 64 kilonewton meter plus 5 times that, 10 carry 1, 5 times that is 21 kilonewton meter. That gives us 21. We can add that. 21 plus 10 is 31. 31 plus 64 is equal to F times 4.2. And then this will be 5, and that will be 9. .2 meters. Here I have kilonewton per meter. Therefore, F will equal to 95 divide by 4.2 divide both sides by 4.2 meters here. Here I have kilonewton meter. That gives you 22.62. That will give you 22.62 kilonewton. So it means the amount of force here should be 22.62 kilonewton. I think that suffices. We will have a look at some questions when we treat tutorials, and when we continue with the moments, taking them to a next level. I think that's enough for this day, and goodbye.